Now, just to wrap this up so I can move on to those other topics today, is we also have some things, and real quick, let's just do this real fast. From the general form, we're able to see the y-intercept. R0 is negative 4 over 2, which is negative 2, so we have a y-intercept at negative 2. Easy, from the general form. From the factored form, we can see, from the factored form here, we can see the zeros at 4, 0, and at negative 1, 0. And I'm hoping you're pretty good with this stuff by now, what I'm just doing. And we also can see a vertical asymptote. So here are our zeros, and we have our vertical asymptote equation, which is x equals negative 2. Last but not least is the picture. So keep in mind, here's our oblique asymptote right here. And so let me erase down here and tuck in the final sketch. We have minus 1, 0 is a point on the graph. We have a 1 over at 4, 0. We have a vertical asymptote at negative 2. Always label it on the graph, which I've said probably 10 times during class. And we have an oblique asymptote, which is x minus 5, which is a line looking like, uh-oh, having trouble here. I'm going to erase this information. And so out here at 5 is our there, and we have a slope of, looking like that off the bottom of the board. Okay? Now, what's the pretty picture look like? We could draw the wiggle diagrams like I showed you last week. Draw a picture of the numerator, draw a picture of the denominator, and then play the plus-minus game. Here's another approach. Let's say I'm right near the vertical asymptote. Let's say I'm at minus 1.9. At minus 1.9, look at the factored form. Minus 1.9, this term is negative. Minus 1.9, that term is negative. Minus 1.9, this term is positive. The ratio of those near the asymptote here is positive. You with me? I'm looking at the factors, using a little dummy number like minus 1.9 that's in here close. Everybody follow me? Carmen? Okay, good. So this is positive. So what that means the graph does near vertical asymptotes blows up or down. It has to blow up because it's positive here. It has to come through this 0. Got a y-intercept at negative 2, which is right in here. Right? So what's the graph going to do? What do you think? Keep going. Help me. Through here. Probably does what from there? Keep going. This is exciting. Probably bottoms out, comes back up through that 0, and then comes in for a landing, sort of. Never actually touches it, but comes in close above it out there. What about off to the left for a complete graph? If you're a little bit to the left of negative 2, let's say you're over here at negative 3. Look at what the factored form tells you. Negative 3 going in here, we have a negative. Negative 3 in here is negative. Negative 3 in here is negative. The result is a Halloween face, like a pumpkin or something, okay? Negative, right? Which means it blows downward here, doesn't it? Has to blow downward. Has to blow downward on the left side of this. Well, where's the rest of the graph? It's down there on the floor because I didn't draw my drawing accurately enough. So that means I'm going to have to tuck it in over here. Sorry about this. Here's the asymptote. Here's the other asymptote. So the other part of this graph ends up being over here like this. So notice that wing of this thing is only a part of it. It doesn't capture all of the character. You also have to make sure your window is low enough to be able to capture this portion that's off to the left over here. Okay, that in 15 minutes summarizes really actually most of the essence of rational functions, but also includes this idea of an oblique or slant asymptote. Next topic. This is something I've only seen once partially done in a textbook years ago and never seen it in any other textbooks. It's called, I like to call it, reciprocal functions in relationships. So, you know what a reciprocal is? First of all, let's make sure we know what a reciprocal is. Well, not opposite. Now, in math, opposite means change the sign of it. Like plus 5's opposite would be negative 5.
Reciprocals, whatever you need to times it to get 1 as a product.
Okay, if you took a number or something times its reciprocal, the product would be 1. Is that what you were going to say?
I was going to say you had 1/2 reciprocal of 2.
Good. As an example, 1/2's reciprocal is 2. Okay? 1,000's reciprocal is 1/1,000. Now, what happens if something's increasing? Let's say you have a function f of x that's increasing. What's the reciprocal going to be doing? Let's see if we can do some of this stuff in words first. If something's increasing in value means it's rising, what about its reciprocal? Doesn't it make sense it'd be decreasing? Okay, what if something is positive? What about its reciprocal? Now, why are we changing signs? Okay, watch. Here's what Todd mentioned earlier. If you take something times its reciprocal, the product has to equal 1. If something was positive and you multiplied it times its reciprocal, isn't that reciprocal still positive? Right? Yeah. And then the product would be still 1, wouldn't it? Okay. Okay. What's the reciprocal of 1? Still 1. Reciprocal of negative 1? Negative 1. You getting the idea? What happens if something's decreasing graphically? Decreasing. The reciprocal would be increasing. So I sort of observed this years ago when I first started teaching, and yet I never found it in any textbook. So what I did is I made up a summary of some of these items, and you're going to find this really useful for sketching purposes if you ever have to draw something called a reciprocal. Before I put that up on the screen, what do we call our reciprocal function? What do we call our reciprocal function in algebra? We did it. It's in our library. It's 1 over x. It's 1 over x. This is actually going to be a good example of leading us into this idea of composite or composition of functions. Okay, so this is called our fundamental reciprocal function. It's in our library, and it should be in our brain. And its sketch looks like this. Looks like that. Everybody have that in their head? Now look at its behavior. What's the reciprocal of 1 over x? It's y equals x, isn't it? Y equals x. And we all know what that looks like. Let me draw it on here dotted. Let's make some observations about what we just talked about a moment ago. Here is a function, y equals x. Here's its reciprocal, 1 over x. Both pictures are shown here. Okay? Notice y equals x, increasing function. Observe the reciprocal, a decreasing function. Right? A decreasing function. everywhere. What's the reciprocal of 1? Here's your value 1 right there. What's the reciprocal of 1? Stays 1. Increasing becomes decreasing. Increasing over here becomes decreasing. Heading towards infinity, right? Isn't this heading up towards infinity? What happens to the reciprocals of those? Heading towards 0, huh? Heading towards negative infinity, the reciprocal heading towards 0 from the negative side. What about a function like y equals x that happens to have a 0? What's the reciprocal of 0? Reciprocal of 0. 0 here, 1 over 0, undefined, vertical asymptote. See it? There's all these patterns, really interesting patterns that exist. And then I gave you a handout, which I now have the top part of the page shown here so you can see it on the DVD, is relationships between functions and their reciprocals. Positives stay positive. Negatives stay negative. Zeros, x-intercepts, become vertical asymptotes. If you started with a vertical asymptote, the reciprocal of that's going to give you a 0. 1 equals 1. 1 stays 1. Negative 1 stays minus negative 1. Increasing becomes decreasing and vice versa. Oh, check this out. Even function in the original that's reciprocal stays even. An odd function like that y equals x is odd. Its reciprocal is the reciprocal function 1 over x. It stays odd. If something's symmetric about a particular x location, the reciprocal will stay symmetric about that. And then here's some, oh, I'm sorry, I went off the bottom of my image. Let me move up here so that people can see on the DVD the rest of this. I kept on talking. Even stays even, odd stays odd, symmetric about some x location stays symmetric. Approaching positive or negative infinity approaches a 0. Approaching a 0 becomes positive or negative infinity. Local maximum becomes a local minimum, usually. Local minimum becomes a local maximum, usually. Let's do a real quick, I gave you another handout with some hand sketches that I had done. Let's see if this shows up on the overhead or on the computer DVD stuff. Is that image readable on the, for you guys? So? Okay, I better go a little, I'm going to just come in on the picture and skip the writing there so that people can see this on the DVD. Okay. Look at what we have here. Here is a function y equals, let's say I took the parabola, y equals x squared plus 2x minus 8. You can see it on the top up here. So here's the parabola. You can see that parabola decreasing and then an increasing image. Notice that the zeros of the parabola become vertical asymptotes. See the parts, everybody? Decreasing becomes increasing. Approaching infinity off to the left approaches 0 off to the left. 1, a value of 1 stays 1. Somewhere out here this parabola has a value, y value of 1, and that means the reciprocal must have a value of 1. And the 0 becomes a vertical asymptote. A minimum becomes a maximum. Symmetry of the parabola about minus 1's location, x equals minus 1, see that? Look at this rational function, folks. It's got symmetry about that y x equals minus 1 value. So if you ever see something strange, and I'll offer some nice examples later in the course, written as a reciprocal, then if you investigate what this thing is first here, then you can use that to draw the reciprocal. Okay, so you have the summary in writing, and I showed the different relationships on the DVD as well. So try to look for those things as you move along through math or applied math courses. Any questions on that? Might take a little bit of practice for you to see it, but just play with it a little bit and you'll be pretty good with it. Okay, let's spend the rest of the time today talking about composite functions or composition of functions. And this is something you've actually already done before. You just didn't realize it. Okay, so we're going to talk about composition of functions. Now, when you take an English composition course, you learn, prior to taking an English composition course, you learn things like sentence structure, how to design a paragraph, how to have one paragraph transition into another paragraph so that you come up with a final composition that makes sense and makes a point. Okay? We do the same thing in math. So what we want to do is to be able to take something that is a function and we want to compose it with other functions.